Okay, so Boolean algebra on digital signals. A digital signal's Boolean variable values, 1 and 0, are isomorphic to propositional calculus, or sometimes called propositional logics, truth table or truth values, true and false. So this symbol is the true symbol, this symbol is the false symbol. Did any of you in your philosophy requirement take logic by chance?
We did study that.
Did you?
At school, it's like when we are taking an exam to go into the school,
Mm-hmm.
you have to do the logic exam.
Ah.
Like they give you different pattern to identify the next one, something like this.
That's cool. Yeah.
And it's tough.
So we're going to do some logic here, which is, we are going to, I mean, you could spend an entire semester easily studying, I mean, you could spend an entire life studying logic. It's pretty cool. There's a lot to it. But we will dabble in logic in this class. Just dabble. We're dangerous like that. We do a lot of dabbling in a lot of things in this class. So we'll dabble, as per usual. Similarly, Boolean algebra, also called Boolean logic, operations are isomorphic to propositional calculus operations, such as not, with its symbol, with this weird symbol, and, with this symbol, and or, with that symbol. Table 4.2 is a truth table for a number of Boolean algebra operators. So let's just take a look, because this is something that I feel like we probably have seen before, all of us, some of these things,
Yes.
but the extent to which we've seen them and our comfort levels probably all vary. So let's talk about this table for a minute. I don't expect us to be able to understand all of these at a deep level, but I think that, all of it's logical, so we should be able to get it. So a truth table is something that is very nice for defining and also clarifying different logic operations. So we start off with these operation inputs, so P and Q, so proposition, so P and Q, and they have Boolean values 0 or 1. So they're either true or false, okay? I could have done true and false symbols in here, but I thought the zeros and ones looked better, looked easier. Did you forget something? Feel free to. So we've got these Boolean values for P and Q, 0 and 1, true or false, right? Or false and true, I guess, 0 and 1. So we have P and we have Q. So there are 4 possibilities, right? P is 0 and Q is 0. P is 0, Q is 1. P is 1, Q is 0. Or P and Q are both 1. Okay, those are the 4 possible things for our 2 statements. The first column of the outputs is the not column, okay? And so we're just going to only take one of the inputs in this case. We're just going to look at P. So not P is the first thing we're going to do. So P in the first row is 0. So not P just flips that bit, okay? So if it's a 0, it gives you a 1. In its first 2 cases, it gives you a 1.
These two are like enemy, not me, it's you.
Yeah, exactly, exactly. So if it's a 1, it's a 0. It's a contrarian, right?
Yeah.
We've all had that friend. So if it's a 1, it's a 0. So that's our not column. So that's the most basic of the logic operators, is the not operator. And so let's go through the other columns then. The and operator, we start using two inputs, two statements now, P and Q. So P and Q is when they're both false, it's also false. So P and Q, if neither P nor Q, then P and Q is false. If only one is true, and is still false, right?
It's like multiplication of 0.
Yeah, it's like multiplication. You can think of it as multiplication. I didn't present it that way, but you can, and it is useful to think of and as being multiplication. I don't like it to think of it as multiplication because and we also use to mean plus in our language. If you like say like 5 and 2, we don't mean multiply. We mean add, so it's confusing. But yeah, so you can think of the and logical operator as being a multiplication of the two. So the only time that it's true is when both of them are true. Or is true if either of them is true. So either P or Q. And then the only time that it's false is when neither P nor Q is true. Okay. Then so this first three we're pretty comfortable with. Like just like basic concepts of logic. Confident we all could do these ones without any trouble. The rest of them are a little weird, but they're not too bad. So let's see how we do with them. So there's the NAND gate. And the NAND gate is, if you look at AND, which is this one, and you look at NAND, you see that they're flipped. So it's the not AND. So you do and then you do not, and you get NAND. Not so bad. Okay. The symbol we use is the up arrow. NOR is not OR. So we have OR, 0, 1, 1, 1, and NOR is just not all of that. So 1, 0, 0, 0. Not too bad either. The last two freak people out a little bit, but it's not so bad. Okay, so I think that the way that I would present this is, so XOR is the first one. If you look at OR and you're saying, okay, OR between, so 0 and 0 is P or Q? No, it's 0, 0. So false. So for false for OR. When you look at it for these two, it's like, is 0 or is 1? True. 1 is. When P is 1 and Q is 0, and you say either? Yes. Okay, so one of them is. But this last one's kind of weird. It says, is it or? So either this or that. Yes. Yes. So the or operator says yes. Okay, that's true. But the exclusive or says, no, that's not what we mean. We meant just one or the other, not both. Okay, that's the exclusive or. It says they have to be different. So one has to be true and the other one has to be false for this to be true. That's the XOR. And the XNOR is the same thing, but for neither. So essentially you can think of it as being XOR and then not of XOR. So you flip all of them. So it's exclusively when they match each other. So it has to be either both zeros or both ones that it's true. If they're not matched, to hell with you. False. Okay. So that's the truth table for logic operations. And, you know, these two P and Q propositions, one being true, one being false, and combining them in this algebra that we're kind of developing is, it's like a whole field, it's a whole thing. So we can do similar stuff like that on signals, too. So that's what we'll do. Digital electronics instantiate these operators. So and, or, not, etc., as logic gates, sometimes as subcircuits of CPUs, and sometimes as discrete integrated circuits for incorporation on a prototyping board, as we'll do in Lab 5. And eventually on a printed circuit board. So when we do it on a prototyping board like we'll do in the lab, like that's great, we'll put in like a chip that's going to have some of these gates on it, and we'll use its pins and whatever, and that's prototyping board. But eventually, if it's going to be in our final design, we wouldn't have it on a breadboard or a prototyping board. It'll be on a printed circuit board, right? So it'd be on like a green board, a motherboard, right? The simplest gate is the NOT gate, which has the following circuit symbol. So it performs the NOT operation. P goes in, not P comes out. So, oh man, there's a Trump joke in there. I'm going to not go there. Okay, so if P is 0, then not P is 1. If P is 1, this is bad.
Can't be worse than that video I posted on random.
I don't think I watched it.
Oh, pretty funny.
Okay, I'll watch it. So it switches it, right? If it's 0, it's 1. If it's 1, it's 0. So that's a pretty simple gate. And actually, that's what I instantiated. I didn't have a NOT gate integrated circuit handy, but I'm forgetting the numbers of the computers now. The one that's on the right-hand side, if you're in the corner in the lab,
Yeah, the corner. That one.
3.
You didn't indicate the NOT gate one.
I put a NOT gate on it, but I made it using a transistor, which you can do. It's fun. I thought I was going to show you guys, and then there were too many things, so I didn't. Yeah, but there also you can buy integrated circuits that are chips that do this too. There are also lots and lots of them in a processor, as little tiny subcircuits in the processor. This gate accepts digital signal represented by Boolean variable P and returns not P. So P equals 1 implies not P equals 0, and P equals 0 implies not P equals 1. Most gates have 2 inputs. So the NOT gate only has 1. Most gates have 2, though. So for instance, the OR gate, which has circuit symbol as shown, takes P and Q in, and P or Q comes out. So it accepts digital signals with Boolean variables P and Q and returns P or Q. Table 4.3 summarizes logic gates and their associated Boolean algebra operators. So let's look at this. So once again, we have all of our different kinds of logic, all of our different symbols, same ones that were in this table here. I've included the gate symbol associated with each one, which honestly, a lot of times I have to look up because I don't look at these all the time. So if you don't look at them all the time, it's hard to remember which one, because they all look, I don't know if you've noticed, they're pretty similar. The one thing that is nice to keep in mind is that the not ones have the little circle on the output. So that's really helpful, because it actually, look at the AND one and look at the NAND one. They're identical, but there's this little circle on the output. Remember that the NOT gate has that circle. And remember that any of these NOT ones are essentially the other operation and then NOT at the end. So NAND, NOR, and XNOR are all easier to identify because of the circle at the end and the NOT aspect of it. And then the X ones have this double input line. One other note on these symbols, these are the American symbols, but sometimes they're called European, but I think they also called the international symbols. They're not these. Totally different. They are, I think they're all like rectangular boxes, and then they have different symbols in them that tell you what they mean. I don't know. I kind of like these better, but also since we're in America, this is what we'll use. But I do use SI units almost exclusively because I hate English units. Worst. Okay. I also have this another nice column here that I liked, and that is how to instantiate each of these in C code. So depending on the situation, you could even do a virtual NAND gate or something like that in your code, right? So maybe you're looking at two different digital inputs, and you want to know NAND on those two. Well, instead of having to actually put in a circuit there, you can do that in C by using this, which makes sense. I mean, these make sense. So the AND is this, the OR is this, the NAND is that, the NOR is that. Those all make sense. The XOR and XNOR they're like not, like I wouldn't have, it took me a few minutes of thinking about it before I was like, yeah, it's not that bad. But XOR gives you not equals, and XNOR gives you equals. It's just pretty cool. So, something to keep in mind. Anything else? Oh, there are also symbols and symbol just pipe. And there's also, instead of that not, there's also this other symbol, the tilde. And just a note on these do similar things. So this one does do not, this one does do and this one does do or. But these are specifically bitwise versions of those operators. And in the discussion of lab exercise 5, the video I already posted, there is some bitwise logic that happens. It's just like kind of convenient how it works. And sometimes we'll use bitwise operators, mostly when we're using bit flags, right? And I had the whole discussion of bit flags. But when you're using bit flags, using bitwise operators sometimes is useful. The double versions of them are the logical ones. They operate on Boolean values. These ones operate bitwise, and so that's a different thing. So it's important not to mix it up. In fact, you guys remember the bug that I found in some code from a couple labs ago. I guess it was the I don't remember which lab it was, but I remember I found a bug in some of the C code for the lab that I was given, and it was exactly this bug. It was that this not was used instead of this not. That was the bug that was in there, and it caused no shortage of hell for me for a little while. It was fine. It worked out in the end, but it did take me a long time to debug that. So, yeah, that was good times. Yeah, because, well, you look at it and you're like, oh, well, it says not that, and then you forget that. And then it's, to add to the confusion, in MATLAB, that is the Boolean logical not, and not the bitwise one. So, yeah, you just can't win. That's the moral of the story. Okay, so this is we went through all the gates. So they're cool, the different gates, the C instantiation, the logic. We're going to use this in Lab 5 at the very end, right? And so it makes sense to just sort of tack this on to the discussion. So I'll open that up. I didn't do it. Here. Let's just discuss where this comes in. It comes in the debouncing circuit, right? B. So yeah. So remember, when we first connect up the switch, so you guys are going to have to do a little bit of wiring or rewiring on the breadboard because when you first connect it up, you want your DIO to be connected directly to the switch and deal with the fact that there's this bouncing that happens, and it's going to cause you problems. And, when you're debugging it, it's kind of up to you. You can either do that, or you can connect it to the debouncing circuit first and then see what it looks like without it next. Kind of up to you how you do it, but I want you to look at both. In the other case, you're going to use this chip here, and it's got 4 of these NAND gates. Right? And now we've talked about NAND gates, so now we can talk about how this thing works. So we've got 4. We don't need 4. We only need 2. But we'll connect up and use any 2 of them to in the form shown here. So these resistors are already on the breadboard for you. And they're already connected to 5 volts, and they're already connected. Actually, do specifically use the two NAND gates that they're connected up to, so you don't have to rewire that part. So you're going to connect. You have to do the connection here to A and to B, and then you're going to have to do this connection here, the Q connections as well. So you have 4 wires to place yourself. So use the jumpers to do it. But let's say, so why does this work? So the idea is that when you press the button, you don't get this mechanical bouncing that happens where you get connection, no connection, connection, no connection a bunch of times while you when you hit the button. So let's just take a look. Let's think maybe I'm just trying to think of the best way to talk about this. Let's just look at these 2 signals. Let's look at A and B. So the way I think I'm visualizing this best is to look at A digital signal and look at B and look at Q, and then look at, and you guys, I'm going to start you guys on looking at Q and Q star, but I'm not going to do the whole thing because I feel like there's an aha that I want you guys to get on your own and not have me like spoon feed it to you too much, because I think it's really cool. So Q star. So AB, it's like a whole meeting happening out there. So AB, Q, and Q star. So let's say that we start out in this switch position that's shown here before it closes. Okay, so say we start out there. Then we're going to have A be connected to this 5-volt supply through a resistor into something high impedance input. So essentially it'll be at 5 volts, A will be, start. And B is going to be connected to ground, right, through the switch. So B will be connected to ground. And then you need to look at what Q and Q star are going to be. What's interesting, one of the interesting things is that Q and Q star, it's indeterminate at this first step which is in what position. So let's just start it out as being Q being low. But we'll have a discussion about why, if that matters or not. And then Q star, so remember these are not AND gates, right? So let's review what a not AND gate does. So not AND gate is and then not, right? And if we look at the truth table, a NAND gate it's the opposite of AND. So it's true whenever they're not both true. Okay? So the only time that it's false is when both are true. Okay? The only time when it's 0 is when both are true. So if B starts out as false, it doesn't even matter what Q is. Q star is going to be true. And that's part of why this indeterminate value of Q doesn't matter. It doesn't matter what Q starts out at because Q star has one of its. So if we know that B is low, then at one of the we know that P or Q, if one of them is low, if any of them is low, all of these NAND ones are true. So it's going to have to be true. Okay. So this is what we start out with. Now, what we're interested to do is so Q star, hopefully, is going to go from high to low one time when we hit this thing, right? And so what happens? This switch mechanically moves over to this position, closed, right? It leaves, it leaves contact with B, right? That's the first thing it does. It disconnects this, which means that B is no longer connected to ground. It's connected to this 5 volts with this pull-up resistor, right? So it'll be at 5 volts. It's no current's flowing on this side, so it'll just be at 5 volts. High impedance inputs, remember. So B will be at 5 volts. So it'll be high when we leave. So we'll say B goes up to high. And when we make contact, then, boom, then A goes low, right? So let's, I'll put a little, I'll even put that that little delay in, like in between, like when you're pushing the button. Okay. So A hasn't made contact yet, and I'll make some vertical lines to like guide us. Okay. I'll make a few. That'll probably be enough. Okay. So our B goes high. So Q star, nothing's. So let's see. So let's talk about A. So A is nothing, and then once you make contact with A, it goes low, right? Boom. Once it makes contact with A. But then it bounces, right? It bounces off. It doesn't bounce all the way back to connecting to B. It bounces on A, though. So it'll sort of have this and you'll be able to see this on the oscilloscope, which is kind of cool. So you'll be able to see this. They won't be evenly spaced like this. I shouldn't have made this so evenly spaced, but it'll do this bouncing before it finally settles in and pulls A low for good. Okay. Oh wait, I was supposed to wait until. I forgot that I was taking a count in between there. You know, you do something you didn't plan, thinking, oh yeah, this will be fine, no problem, and then you're wrong. This is my experience. And then I'll make one more of these. Yeah, so it leaves B. B goes high. And B is gonna actually stay high, right? Okay. And good. And then yeah. So Q started low, and once we've got, so when we look at, we can look at Q to find out what Q is. You have to look at what Q star is and what A is, right? So Q is going to depend on A. And if anything, remember, if anything is low, because it's the NAND gate, right? So if anything is low, then it's true. Okay. So started off, Q star is high. A is high. So Q is low. Then A goes low, right? So Q's fine here. A goes low then, and so if anything going in here is low, then Q goes high, right? So Q goes up. Q star it depends on Q, right? So it depends on it. If anything here is low, so B went high, but Q is still low for this, right? But as soon as Q goes high, Q star has got to drop, okay? Because Q is now high, and B is now high, and that's the only case where Q star is 0, right? Is when both of them are high. Now, Q is high, and we'll have to look at what happens now. Q star is low, so Q is going to be high, and anything being, so, and A is going to go back and forth to low. So I don't want to go through the whole thing, because otherwise, because this is part of like the exercise that I ask you guys to do. But essentially, this makes it so there's only one clean transition here, but I want you guys to, I was like, I'm going to go a little ways, and then I got kind of caught up. I don't want to go this far. So do the rest of it. Justify why Q star only has the one transition. I want you to explain it to me in a way that is your own words. I mean, I didn't provide a lot of text in it, so that's good. So like, explain to me why this transition happens, and draw a graph like this that explains it. That should help quite a bit. So, okay, lest I continue, because this is the next part. This is like the last part. But it essentially uses the fact, and this is, so the one thing I do want to say is when you see this last little move, when you work through it, what you find is that there's, for the first time, this is like the simplest circuit, or one of the simplest circuits, where there's memory involved. So A going from low to high the second time doesn't matter. And it only doesn't matter because this double NAND gate allows it introduces memory into this circuit. It knows what the previous state was, which is weird, because the NAND gates alone, they don't care. They're continuously updating. But when you connect them like this, they actually have a memory for how the signal changed. So it's pretty cool. The fact that there's memory in it for the first time, I think is really it's like a cool aha moment. I'm like, oh, this is how, this is the building block of how the actual processing happens. When you want to do like an AND operation, you want to do an OR operation. There's like literally these digital circuits are doing those in a computer, in a processor. So it's cool to see that happen and see a little bit of memory emerge in this as well. And yeah, and to see how useful it is in this debouncing circuit. Like, if it wasn't for this trick, it's kind of a trick, you would be stuck having to be really clever with like your digital signal processing as you're updating things. You wouldn't be able to expect one nice clean transition. You have to worry about it in your program, essentially. If you hit a button, you would have to be expecting that to happen, and you'd have to work out logic in your program. Instead, so you could do like a digital debouncing, right? Or like you could do a programmatic software-based debouncing, where you could do the same logic in C, right? Or this is in the previous lecture. You could use a combination of logic like you do in C there. Totally software-based. And sometimes maybe that's the best solution, but you can build that circuit in hardware and then guarantee that you don't have to worry about it in software at all. So that's what we're doing. We're doing it in a hardware place. If you can do it in hardware, it's great. Sometimes it's cheaper to do it in software, so we would just do it in software. So like, for instance, say you're making a device, like product that's a user interface includes some buttons, okay? And you want to, you're looking at you're looking at whether you want to do a debouncing circuit on the button, or if you want to do it in software. That's a design consideration, because if you do it in software, you have to have potentially a more powerful computer to run your software, because you're going to have to add complexity to it. You're going to have a little bit more memory, a little bit more processing required. Maybe that's totally fine. It's definitely going to be cheaper if you don't have to upgrade. Maybe you have extra processing and memory for your application, so using a little bit to do a debouncing routine is fine. Maybe it costs an extra, whatever it is per unit to add a debouncing circuit in there, and that is a nice way to do it. Say, okay, I'm going to do it in software. But maybe in hardware it's better. Maybe in hardware you already have to have a custom PCB that you're going to be including. It's like maybe a very small corner of your PCB where you have your debouncing circuit, and there's not a lot of extra cost, I guess, per unit, and so you include it on the board. So it's sort of like it's like you could do it either way, but it's good to think, like, to recognize you have those options, right? You could either do it on the board, or you could do it in software. So, okay. Does everybody get the lab application of this? I want to make sure we got the lab side. How we're going to do it. You have to connect the 4 wires. So each of the cross wires, and then the A and the B wire. Okay. Let's walk over to the lab then, unless there are other questions.